My name is Julia Ling, and I'm really excited to be here today to talk to you about machine learning for scientific applications. I'm currently the CTO at Citrine Informatics, a Bay Area startup applying machine learning to materials and chemicals development to try to accelerate the development and deployment of new high-performance materials. And prior to Citrine, I was at Sandia National Labs, applying machine learning to turbulence modeling. So one of the defining themes of my career has been applying machine learning to different scientific R&D applications. And I just think it's a tremendously fun space to be in. So I'm really excited to talk to you about why it's hard, what some of the challenges are, and also why I think it's so much fun. So I'll start with why it's hard. When you think about conventional machine learning applications, often one of the first things you think of is big data, right? That's one of the critical buzzwords. You think about having millions, billions, or more data points. But in scientific applications, that's an exception. Typically, you're talking about small data. So I've worked on projects with just dozens of data points, sometimes hundreds. And that comes with a whole host of different challenges and approaches to try to surmount having smaller data sets. In conventional machine learning applications, these are often defined by having very repetitive tasks. So if I build a classifier to try to classify cat images versus dog images, I'll train it on cat and dog images, and then I'll deploy it to classify cat and dog images. I wouldn't take a cat and dog classifier and then use it to try to classify horses and cows. But in scientific R&D applications, that's exactly what we're doing much of the time. Science is about the act of discovery. You're not doing the same thing over and over again. You're often trying something new. So how can you use machine learning when you're trying to try out something new? And then the third key challenge I want to talk about is the fact that in conventional machine learning applications, you're often trying to automate as much as possible. So if Amazon recommends me a book, it's not because some literature expert is on the other side thinking about what Julia might want to read next. It's all automated. But scientists like to be involved in the process. They're curious people. They want to be engaged. And so that requires a very different workflow when you want to have people in the loop with it. So those are all the reasons why it's hard. Why is it fun? Well, spoiler alert, it's all the same reasons. It's fun because you can't just use an off-the-shelf approach as a black box. It's fun because you have to get your hands dirty. You have to learn some of the science. And that makes it just a really enriching experience. Beyond that, it's also really satisfying because in many cases, the applications are impactful. One of the key things we're doing at Citrine is trying to help accelerate the development of more sustainable materials. And when you get to work on machine learning models that can have that kind of impact, that's also really satisfying. So one of the things I wanted to do in this talk is I'm going to go through each of these different challenges and talk about both going into more detail on what the challenge is for these three different challenges, and then some of the solutions I've seen work. Now, I'm not going to pretend at all that the approaches I discuss are comprehensive and that there's no other ways you can tackle these challenges. These are just some of the approaches I've seen work during my career. So after I go through each of these three different categories, I'm going to then talk about two different case studies from real-world use cases of machine learning for scientific R&D applications so that we can see how these different approaches play out in real use cases. So I'm going to start with the data challenge, which is appropriate because machine learning always starts with the data. Now, there's a variety of different ways that the data challenge manifests in scientific applications. And the first is messy data. Now, scientific R&D data, for anyone in the audience who's ever done a PhD in experimental science or has worked with the scientific data, you'll probably be familiar with the fact that it can get really messy. People will make handwritten notes in lab journals. Maybe there'll be several different tracking systems across a company, and they may not even have linked sample IDs. Sometimes data is locked into PDFs, like this one on the right, this data sheet, or you might have a variety of different extremely specialized spreadsheets that are hard to pull together. And when you're using a data-driven method, it's really problematic if you can't even access your data, if you can't even pull it all together. The next challenge I already referenced, which is the small data challenge. If you look at a traditional application like image classification, one of the real keystone data sets is ImageNet. ImageNet has 14 million images, and it was considered a major milestone when this data set was created. It took 2.5 years to complete, and during that time, each label cost a few pennies. This was done through Amazon Mechanical Turk, and a given labeler could give about 50 labels per minute. So it did take 2.5 years to create. It was considered a real monumental achievement, but that's nothing compared to the challenge of trying to create a scientific R&D data set. We've had customers start with fewer than 40 data points, and it's really common for them to just have hundreds of data points. And that's because experiments can cost tens of thousands of dollars to run and take months. So if you compare that to 50 labels per minute and pennies per label, you can see why these companies can't compile massive data sets. It's just too costly and too time consuming. And so when you're working with data sets like this, smaller data sets that were so expensive to generate, you have to be really careful with it. You have to realize how valuable this data is and make sure you're using it as efficiently as possible. A third challenge is that the data in scientific applications tends to be extremely sample biased. Now, sample bias in data is pervasive across a lot of different applications, but there's a couple different common themes in scientific data. The first is that the data are often collected in clusters or in lines. So a scientist might find a high-performing point and try a whole bunch of points neighboring that, or they might just vary a single parameter at a time. The result is that you don't get a very uniformly distributed training data set. Even more problematic is the fact that negative results are rarely published and sometimes not even retained internally. So if you look at the plot on the right here, this is a plot that shows both of these different problems. This is from Wikipedia, a plot of different superconductors. And each different color here represents a different family of superconductors. And what you can see is that they tend to be very clustered. There's a lot of different ones of these families that have very similar materials. And the other thing you can notice is not only is it clustered, but of course, the only things on this plot are things that are superconductors. So if I trained a machine learning model on this data set, my model would predict that every single material is a superconductor because that's all it's ever seen. And that obviously wouldn't be a very useful machine learning model. So it's really important when you're applying machine learning to scientific data sets to be aware of this kind of sample bias. The last challenge I want to talk about on the data side for scientific data is siloed data. Now, this is unfortunately quite common both in academia and in industry, though for different reasons. In academia, data are often hoarded so that groups can publish successive papers without being scooped on the same data set. Furthermore, once a grad student graduates, often the data that they were responsible for generating becomes inaccessible. Not all grad students are very meticulous about making sure their data sets are saved in such a way that future researchers can leverage them. In industry, they have their own set of problems. Data sets tend to be strictly guarded between competitive companies. If two companies are trying to both create the same kind of material, they're going to guard their secrets very closely. So you can just think about, the famous secret recipe for Coca-Cola. There's no way they want that falling in the hands of Pepsi. Even within a company, different business units might not share data with each other. And even within a business unit, different teams may just be unaware of relevant data sets on other teams. And so this is really problematic because in machine learning, of course, you want to be able to bring together all the data possible, especially when you're already working with small data sets. And if different data sources are inaccessible to you, or if you're just unaware of them, then you're going to end up with subpar performance. Okay, so I've led you through some of the different challenges on the data side. Let me now talk to you about some of the different solutions that I've seen work. So I talked about the fact that you have these messy data sets that sometimes they're siloed. One of the key solutions to that is just careful data curation. This is something that takes time, it takes care. But what you can do is you can link together all those different data sources to come up with a comprehensive data set that can actually be used for analysis. The example here is from materials development. This is a data format on the Citrine platform that lets you link together data from procurement, from processing, and from characterization together. And so different people in different departments might be collecting, data in the procurement department about initial ingredient purity, and then maybe you'll have some temperature sensor data during processing. And then finally, you might have some characterization data on the final materials performance. And in order to actually run machine learning on this data set, you have to link all of those different data sources together, even if those data sets were collected by different people in different departments, maybe in different locations. So careful data curation becomes extremely important. Beyond that, to overcome the small data challenge, one of the key tools in the tool belt is domain knowledge integration. And this is actually one of my favorites. I come from a scientific background, and so it's really satisfying to me when I get to apply scientific principles in machine learning workflows. And the underlying reasoning here is that if you don't have much data, you really can't afford to waste any of it. My own philosophy when I'm approaching applying machine learning to a scientific application is to try to build in everything we possibly know. So talking to the domain experts and then trying to build in analytical relationships, important features, correlations, adjacent data sets. Because if each data point costs you tens of thousands of dollars, you can't afford to be just throwing big data at the problem and hoping that the machine learning model will learn everything itself. You really need to give the machine learning model a leg up and build it a foundation of scientific domain knowledge so that it's just trying to fill in the gaps of things we don't already know instead of wasting all that data relearning the basics. The example on the right here is an example from material science. In this case, we wanted to be able to predict an experimental bandgap property. We had a limited amount of experimental data and a much larger data set of computational data. Now, that computational data was less accurate than the experimental data, but it was much more plentiful. And we knew that it would be correlated. And so we built a machine learning model that had that computational property as an intermediate, and then use that as an input to a machine learning model for the experimental property we actually cared about. And what we found is that when we added this intermediate step, we got a much more accurate model. So this plot on the right shows the model error as a function of the amount of experimental data. And we see that in black is if we use this intermediate approach, in red is if we do not, and we just go directly to the experimental bandgap. And we see that with 50 data points using this intermediate approach, we get the same accuracy as using about 150 points using the direct approach. So again, when you have limited data, you really want to use all the sources of information available to you to make your models as accurate as possible so that you're not relearning the basics and that you can really use your data efficiently. Another very common technique for when you have limited data is transfer learning. And this is not at all specific to scientific applications. Transfer learning is a really common approach when you have limited data sets across many different disciplines. And the basic idea with transfer learning is if you have a large data set on a related use case, you train your machine learning model on that, and then you just retrain the last few layers of your neural network on the smaller data set that's specific to your use case. So in this case, this is an example where we had different images of titanium microstructures of 4 different types, and we only had 60 images total, so that's nothing. But by leveraging a pre-trained convolutional neural network, we were able to generate a reasonable classifier based off of the fact that we were using transfer learning, that we were using this pre-trained neural network. And then the last approach that I want to bring up is careful cross-validation. Now, this one is a little bit different. This isn't about making your models more accurate. This is about making sure you know how accurate your models are. One of the real problems when you have sample biased data is that it's really easy to fool yourself into thinking that your models are more accurate than they actually are. So for example, if I have the data set here on the right, where I have these very clustered data points, and then I use random cross-validation, then I'll likely think that my model is pretty accurate because for every test point, there's going to be a training point really near it. And so my model will be able to make very good predictions. But then if I actually deployed this model and use it on a new cluster of points that it hasn't seen before, the model accuracy is likely to be much lower than what I would have believed based off of my cross-validation error. And so it's really important when evaluating your model accuracy to bear in mind how the model is going to be used when it's deployed. And when it's going to be deployed, it's going to be used in data that are distributed different than the way your training data are distributed, then you have to make sure that you cross-validate it in a way that's in line with that. So for example, if I thought that I was going to apply this model to look at new clusters, then I should make sure that when I do cross-validation, it's cluster by cluster. Okay, so I've gone through now the first set of challenges and some of the solutions on the data side. Next, I want to turn to the exploration challenge. So this is a very common query we get from customers at Citrine. They'll say, I want to develop a material better than anything in my training set. Now, of course, they're going to have a more specific use case than that. If we're talking to a glass manufacturer, they might say, I want to develop a glass with a higher impact strength than anything I have currently available. Or an alloys manufacturer might say, I need to develop an aluminum alloy with a better strength to weight ratio than anything I have available. But in general, they tend to follow this framework of, I want to develop a material better than anything in my training set. To do so, I'm going to have to explore new regions of parameter space. What they're telling us in essence is that they need to extrapolate. Now, for those of you who are familiar with machine learning, you'll know that machine learning is not traditionally designed for extrapolation. The whole point of machine learning is to train it on a data set so that it can learn this underlying structure in that data set. For example, if I have the training data on the right here, the red dots, I can fit a machine learning model pretty well to the regions where I have that training data. But if I then need to guess what's going to happen in these regions where I don't have any data, the machine learning model doesn't really know what to do there. It's not a physics-based model that can actually extrapolate. It's data-driven, so it needs the data. So what can we do then when the use case is exploration, when scientists want to try new things, and yet we're using a set of techniques that are fundamentally based off of the data we already have? Well, first and foremost, one of the most critical tools when you're looking at an exploratory use case is uncertainty quantification. If you're wading into unknown waters, it's really important you know how out of your depth you are. It's really important that you know how much you're extrapolating. And so uncertainty quantification is basically saying that when your model makes a prediction, it gives you error bars. It tells you how uncertain it is. So for example, on the right here, this is a machine learning prediction that instead of just giving a single value for its prediction, it's giving a distribution. Now, different uncertainty quantification methods might have various ways of presenting that information. In this case, you get a full distribution. In other cases, you might just get a standard deviation. But the outcome is the same in that it's allowing you to know in each of these cases what level of confidence the machine learning model actually has in its prediction. And that means that you can systematically explore. You can say, the user can say, okay, I want to look for regions of very high uncertainty. I really want to try out new areas. And maybe that will teach the machine learning model something new, and it will be able to improve the model accuracy in those unknown regions. Or you can say, no, I want to stay closer to the things I know. I just want to push the boundary a little bit. Now, one of the key facets that you have to look for in your uncertainty estimates in this case is that they be prediction by prediction. For those of you who are coming from a statistics background, that would mean that they're heteroscedastic. Even I have trouble saying that word out loud. In other words, you don't have a uniform uncertainty across your model. You have an uncertainty on a given prediction. So for example, if I'm just using cross-validation error, then that's an uncertainty for the whole model, right? That's just the error of the model in general, and it doesn't vary based off of which test point you're using. But what you need for this kind of exploration is an uncertainty estimate that varies depending on your test point. And there's a few different approaches that enable that. I'm not going to get deep into the details of any of these. You can read up on all of them. They're all very present in the literature. But the key attribute is that they're going to give you a specific uncertainty for each test point so that you know how much you're extrapolating for a given test point. The next attribute that, the next approach for when you're trying to explore is to have iterative workflows. In other words, you have to reset your expectations. When you're exploring, you should not expect to get a hole in one. You know, if exploring is like golfing blindfolded, right? If you don't know where the hole is, then you're not going to get a hole in one. And instead, you should use uncertainty quantification to iteratively explore your parameter space. So you should be able to say, I want to be able to learn in this new region. I'm going to pick a point with high uncertainty. The model will get much smarter once I have that new test point, and it will be able to let me get to my goal as quickly as possible. So in this case, you can see that an active learning approach where you iteratively retrain your model on more and more data is going to potentially reduce the total number of experiments you have to do, but you should not expect to discover your new Nobel Prize winning material or discovery in a single shot. Okay, and then I've saved the best for last. This is really one of my favorite challenges, the scientific user challenge. This is something that I really resonate with because I come from a scientific background. Scientists are unlikely to use a tool they don't trust, and they're unlikely to trust what they don't understand. People get into science because they're curious, because they want to understand. And if you just give them a black box model and say, just use the outcome, and they have no idea where it comes from, that's going to be deeply, deeply unsatisfying to them. And yet, that's really the way machine learning is often presented. It's often presented as this black box. You know, these deep neural networks, don't try to understand them. They have millions of parameters, but they're more accurate than what you can do without them. And that presents a real challenge for adoption, because if you're trying to get scientific users to use these models, that goes against the grain for them. They really want to understand the tools they're using. And then the second one here comes down to just underlying philosophy. For me, I believe that it shouldn't just be the machine learning model that's doing the learning. It should also be the scientist. There should be human learning alongside machine learning. If the machine learning model is actually more accurate than the scientific theories are, or the empirical laws that scientists have been able to come up with are, then we should be able to learn what the machine learning model figured out. We should be able to learn. So how do we go about that? The first approach might seem obvious, but it's just to get the scientist involved early and often. And getting the scientist involved solves two different problems. The first one is domain knowledge integration to mitigate small data. So if you get the scientist involved, they can use their expertise to try to make the machine learning models more accurate by embedding their domain knowledge. And that helps them overcome the fact that they may not have that much data. And the second is that engagement builds trust. As the scientist tinkers, as they try out different things, they get a better sense of how the machine learning model is working, and they're more likely to trust the outcomes and the predictions. The diagram on the right here is a machine learning model from the Citrine platform. Now, I know that the text here is illegible. The point isn't to actually understand everything that's going on in this model, but the thing you should be able to know about this is that the purple boxes are all machine learning models, and then the white and gray boxes are inputs and outputs of the machine learning models. And so what you can see here is that there isn't just a single model, it's this complex graph of models. And this isn't auto-generated by the platform. This is something that scientists can tinker with and build. They can draw different connections to show how different properties might be related to each other. They can add in analytical relations or feature maps that might make sense. And some of those may be automated or suggested by the platform, but the scientist actually has control over what those connections are. And the result is that scientists will play around with this. They'll see what changes the model performance, and that engagement builds trust and it makes the models more accurate. And I want to emphasize that I don't think that model creation is the only stage at which scientists should be involved. This workflow shown here is something we call the sequential learning workflow at Citrine. This is all the stages that a customer would go through between starting off with raw data and then finally at the end getting a suggestion for which experiment they should run next to try to find a material that hits their specifications. And I think that scientists should be involved at every single stage of the pipeline. At data cleaning, the domain experts are often the ones who know what kind of outliers or errors to expect in the data. At data curation, I showed you that graph before of how data can be connected from procurement through processing to characterization. The scientists and the domain experts know the correct way for the data to be represented, to be captured. They know which other data sets might be relevant. I just gave the example of model creation, how you can build in domain knowledge into the models themselves. The design space is the space of all the experiments that the scientist could run. And they're the ones who know, how hot their ovens can go, or how long they can put something in a chemical bath, or what level of lead they're willing to put into their alloy. So they can create that design space and constrain it. They can select how they're going to score which materials are the best, how extrapolatory or exploratory they're willing to be, what they're trying to hit as their targets. And then lastly, they shouldn't just take the output suggestions with blind faith. They should look at them, evaluate them, and if they're not getting suggestions that they think make sense, they should think about why they don't make sense. Maybe they're just extremely creative and they're worth a shot, or maybe they're nonsensical and there's some kind of constraint that they could have entered into the model that they didn't, and they can go back and iterate on this process. So different workflows are going to make sense for different scientific applications. The key takeaway here is that if you can get scientists engaged early and often, it's going to have two major impacts. One is it will often make the eventual outcome better because they'll be able to build in their deep domain expertise into each stage. And the second is that they'll have a lot more trust in the eventual outcome because they've been involved in every step of the process. All right, prediction interpretability is really one of my favorite topics. This is something that I can and have given full lectures on by itself. But fundamentally, prediction interpretability is the idea of having a way of explaining why the model made a given prediction. And if you can explain why the model made a given prediction, then the scientist can learn too. They can validate their hypotheses. They can see why the model prediction might disagree with their own intuition. There's many, many different approaches for prediction interpretability. I'm not going to go into all of them. There's been, whole books written about model interpretability and prediction interpretability, and I highly encourage you to look into them because it's a really fascinating topic. I'll talk about one method that I'm particularly fond of on the right here, which is a sensitivity analysis. In this case, our machine learning model was predicting corrosion resistance of a material, of an alloy, and the prediction for the particular alloy of interest is in red. And then what we've done is we've varied one of the important features, the magnesium fraction in this alloy, and held everything else constant to see what the model predicts for neighboring alloys where that one feature has been varied. And what we can see is that the model predicts that if you decrease the magnesium fraction, then there's a significant drop off in corrosion resistance. And similarly, if you increase copper fraction, then there's also a significant drop off in performance. Now, this is important for two different reasons. The first is it agrees with domain knowledge for this field. It's known that in these alloys, the corrosion resistance improves with magnesium fraction and decreases with copper fraction. So that's validating, right? That increases trust in the model when you see that it agrees with domain expertise. And the second thing is it shows you that this particular alloy, which is predicted to have such good corrosion resistance, is really near a performance cliff in two different directions. So it may not be the most robust solution to this problem. And so again, the key takeaway here is that when you have prediction interpretability, then you start to make it possible to have scientist learning alongside machine learning. Okay, I've gone through now 3 different core areas that can be both challenging and quite a bit of fun, in my opinion, when you're applying machine learning to scientific applications. I've talked about how the data themselves can be challenging and some of the approaches for overcoming it. The nature of having these exploratory tasks, that means that you have to leverage things like uncertainty quantification and iterative workflows. And lastly, I've talked about this idea of getting scientists involved early and often in the process. I want to now shift gears a little bit and talk about 2 different case studies so that you can see how these different approaches play out in real use cases. So the first one I'm going to talk about is from the world of turbulence modeling, and the particular application of interest in this case is jet engines. So this case study draws on the work of a PhD student that I co-advised, Pedro Milani. He's graduated now, but a lot of this work comes from his dissertation. So the context in this use case is that in jet engines, it's critically important to know the turbulent mixing of heat downstream of the combustor, because the hot air coming out of the combustor is actually hotter than the melting point of some of the downstream components. And you definitely don't want those components to melt. So you have to be able to predict the mixing of that hot gas really accurately. And unfortunately, it's extremely difficult to predict. It's extremely difficult to simulate using physics-based simulations. Without getting into all the gory details of the turbulence modeling, one of the key terms in the transport equation is the turbulent scalar flux. So in this case, the goal of the machine learning model was to predict the turbulent scalar flux given the local flow variables like density and velocity. Okay, the data in this case were challenging because we had 4 different high fidelity simulation data sets for 3 different geometries plus a different flow setting. Each of those simulations had millions of different data points, but it was extremely sample biased because points that are near each other in the same simulation are going to be extremely correlated, but very different from that same point in a different simulation. So you've got this extreme case of data clustering. The solution here was just to have very careful cross-validation. This is something that I see going wrong in papers all the time, where people will train and test on the exact same data set on different points in the exact same physics-based simulation. And the problem is, then you have no idea how that approach is going to work in a different use case, in a different flow scenario, or in a different geometry. And so in this case, Pedro's just very careful to make sure that if he trained on one data set, he would test on a different data set, that he was never training and evaluating on the same data set, so that we could see how the models actually generalize between flow cases. In terms of domain knowledge, in this case, one of the key pieces of domain knowledge of interest was something called Galilean invariance. This basically means that physics doesn't care how you draw your coordinate axes. Physics is rotationally and coordinate frame invariant. We were able to build this into the neural network architecture itself. And we used a specific neural network architecture that ensured that Galilean invariance would be enforced on our final scalar flux predictions. This increased both model accuracy and interpretability. as we'll see. So I told you that interpretability was one of my favorite topics, and so this was a case where this interpretability was really one of the major outcomes of this project. What we're looking at here is something that we called point-wise feature usage, which was basically feature importance on a per prediction basis. So these plots are showing contour plots of feature importance in the flow. So this is a slice through the fluid flow. The bottom here represents a turbine blade. So this is a wall. And then everything in color is regions of fluid flow. And the regions of yellow are regions where that particular feature is very important. And the regions where it's darker are regions where that feature is less important. So you can see that this particular input to the machine learning model is very important just in this very small region very near the wall. And one of the key pieces of intuition that we were able to get for scientists out of this was that different features were important in the near wall region than far from the wall. And there were some very specific terms that were important in that near wall region. That means that as we think about what is going on from a physics perspective, we can see which terms matter in which regions, what terms are activated, and that can give us a lot of intuition and teach us a lot about the correct ways to model flows like this. So I really like this example because one of the key outcomes here is scientist learning, and I don't think that that should be devalued just because we're also using machine learning. The second case study I want to talk about is in materials development, specifically in organic semiconductors. So this was a case where Citrine was partnering with Panasonic. And in fact, this use case has already been written up and published, so that's why it can be shared openly. But Panasonic's goal in this case was to develop organic semiconductors with an increased hole mobility. They partnered with Citrine to try to explore this huge design space of potential candidate molecules for their application. And they were using a computational approach called density functional theory to evaluate these molecules for their suitability. All right, so getting into the challenges for this use case. The first challenge was with the data. They started with just 32 data points, just 32 DFT simulations that they'd already performed. Now, the solution here was that they were willing to have this iterative approach. They were willing to use an active learning, or what we call sequential learning approach, to guide the collection of additional data. So what happens in sequential learning is that you train your machine learning model on your initial data set, you use it to score candidate materials, you then run, in this case, the simulation on the top performing predictions. You take that new data and you use it to retrain your machine learning model so that it gets smarter and smarter over time. And in fact, the machine learning model can select points based off of the areas it needs to learn about the most. So this is called sequential learning. It's this iterative approach. It leverages uncertainty quantification for a systematic exploration of the design space. If you start with only 32 data points, you're going to have to extrapolate because you've got so little of the parameter space covered already. So this is one of those cases where uncertainty quantification and an iterative approach were critical. In the end, they collected 196 total data points, so it was never a massive data set, but it did increase significantly over the course of this project. Another key phase in this project was domain knowledge integration. Because they started with a relatively small amount of data, it was really important that they build in their domain knowledge, and they did that in a variety of ways. One of the ways I wanted to talk about was in customizing the design space. Now, again, the design space is the space of molecules that they were willing to try. And initially, we used a design space based off of a public data source that wasn't really tailored to their application. And one of the things that they did is they came back and said, here's some specific characteristics that we think would make molecules most suitable for this kind of application. And so we were able to tailor a design space around those molecules, those attributes. And the analogy I would use for this is we changed which haystack we were looking for needles in, right? In any event, when you're looking for high performing materials, you're looking for needles in a haystack. but it's really critical to know whether or not your haystack actually has needles in it. And by giving us this customized design space, they were making sure that there were there's a much higher needle to hay ratio in this haystack. And it had a big impact for this project. What this plot is showing is the performance on the y-axis of based on the property that they cared about. And on the x-axis is the number of iterations through this iterative workflow, this active learning workflow. And what you can see is that after they switched to using this custom design space, suddenly the performance of the materials they were testing got better and better until they actually were outperforming the best candidates in their training set. And so this was a case where in the end, they were able to patent 4 different candidate materials. And what they really used machine learning to do was to focus down their search, to make it so they didn't have to brute force run simulations on all these different molecules. Machine learning gave them a way to systematically explore this design space. And from a domain knowledge integration standpoint, one of the key takeaways was if you want to find a needle in a haystack, you first have to make sure you're looking at the right haystack. So if you really only walk away from this talk with one key takeaway, it should be that machine learning for scientific applications is fun because it's challenging. It forces you to get your hands dirty. Off-the-shelf approaches as a black box, those just don't work in this use case because of the kind of data you're working with, because of the kind of users you have, because of the nature of the exploration you're trying to do. So this is, to me, this field is just so much fun because you get to combine science and machine learning together, because you get to learn about new scientific domain knowledge and scientific applications, and because you have to work with all the sparse, messy data. All these different challenges are really what makes this application so much fun to work in. And with that, I'd like to just thank you for your time, and I'd be happy to take any questions.